Hi and welcome to this Junior Cycle Higher Level Maths video where we're going to look at geometry and specifically lines and angles. So this video is going to cover an introduction to geometry theorems and terminology, and will include a look at vocabulary, terminology, types of angles, properties of angles and parallel lines cut by a transversal.
So now let's work through some really important geometry vocab that you must know. So you don't need to know these definitions off by heart, but you need to be able to explain them in your own words. So an axiom is a statement which is assumed to be true. It can be accepted without a proof and used as a basis for an argument. Converse means the converse of a theorem is formed by taking the conclusion as the starting point and having the starting point as the conclusion. We'll see a bit more about converse in the second geometry video, which deals with triangles. A corollary follows after a theorem as and is a statement which must be true because of that theorem. Implies indicates a logical relationship between two statements, such that if the first is true, then the second must be true. Is congruent to, two things are said to be congruent if they are identical in both shape and size. We're going to look at congruent in a lot more detail because on the Junior Cert course we specifically looked at congruent triangles, so that will be covered more in the second geometry video on triangles. Is equivalent to. So two things are said to be equivalent if they have the same value but different forms. So some more vocab. A proof is a sequence of statements made up of axioms, assumptions and arguments that follow logically from the preceding one, starting at an axiom, a previously proven theorem, and ending with the statement of the theorem to be proven. So you've had 5 examples of formal proofs which you would have had to learn off for Junior Cert higher level in the geometry section of the course. There'll be new theorems to learn off as we move to Junior Cert, or as we move to Leaving Cert higher level. So a theorem is a statement which has been proved to be true and deduced from axioms by logical arguments. So a theorem is something that requires a proof. We are not required to prove every theorem on the course, but they have picked specific ones for us to look at. So let's jump straight into an example. The following 3 terms are used in geometry: corollary, proof and axiom. Write down write each of these terms in the table below to match an entry to its description. So the first thing is a statement which we accept without proof, and that's called an axiom. A statement that follows easily from a previous statement. So that's a corollary. So we said that that was kind of like an add-on to a theorem or previous proof. And an argument showing that the statement must be true, that itself is our proof. So Salem writes the following statement: if a shape is a square, then it must have 4 right angles. Complete the converse of Salem's statement. So the converse is the opposite. So if a shape has 4 right angles, then the shape is a square. Now, they've asked us something else here. Is the converse of Salem's statement true or false? And the answer is false. Just because you have 4 right angles, does it mean you're a square? No, you could be a rectangle. So yes, if you are a square, you have 4 right angles, but the converse is not true. As we work through our theorems, we're going to see that some theorems have a converse which is true and others do not. So just because it works one way does not mean that it will work the other way. So the justification is it could be a rectangle. Could be a rectangle. Okay. So now let's look at some terminology. So a plane is a flat 2-dimensional surface on which points and lines are drawn. So usually that's going to be your copy, the exam paper, or a whiteboard. So points are a location or a position. So generally in geometry we're given the points, and as we move towards coordinate geometry, those points will be given to us in the form of coordinates so we can identify where the point should lie. So a line is a line that passes through 2 points, goes on forever in both directions. And that's really, really important to remember, that a line goes on forever. So there's two ways that we could name this line here. It could be named by the 2 points which lie on it, A, B, or it could be given a single letter, L. So coplanar describes points that lie on the same plane. Collinear describes 3 or more points that lie on the same line. And 3 or more is important because any 2 points will lie on the same line, because if I draw any 2 points, I can also draw a line that connects them. It's only as we add in the third point or more that we suddenly have a deviation from that. So a line segment is a piece of a line. It is a line that starts at A and ends at B. It's written using square brackets, and it can be written as A to B or B to A. So you can see the two pieces here. It can be written like this or this. A line segment is just a piece of a line, so it starts and it ends. So a ray, which is also known as a half line, starts at a point but goes through a second point. So this line starts at A and it goes through B and it will continue on forever. The notation for this is it starts at A with that square bracket and there's nothing then on the B to imply that it goes on forever. So we can see how this might be called a half line. So the point of intersection is a point where two lines meet. That's going to be very, very important as we move into the coordinate geometry of the line, but we'll also see points of intersection here. So now let's talk about some angles. So we have an acute angle, which is less than 90 degrees, a right angle, which is exactly 90 degrees, an obtuse angle, which is between 90 and 180 degrees, a straight angle, which is 180 degrees, a reflex angle, which is greater than 180 degrees, and a full rotation, which is 360 degrees. So if we were to name an angle, we use 3 letters or a single letter. So there's 3 ways that this angle can be named. The first is CBA, the next is ABC, or simply B. Notice this little symbol here in front of all of them, which means angle. So notice how the angle we want here is at B, and B is always that middle letter. So the arms of the angle are the 2 lines which make up the angle, and the vertex is where they meet. It's that point. So the plural of vertex is vertices. So if we were to move into shapes and talk about a triangle, instead of saying 3 points, we might call them 3 vertices. So now let's talk about some properties of angles that we're going to use to help us to work out missing angles. So the first one is angles at a point add up to 360 degrees. So we can see here that A, B, C, D and E are 5 angles which when put together give us a full rotation. Based on that, I know if I add all of them together, it will be 360 degrees. So angles on a straight line. Angles on a straight line will always add up to 180 degrees. And the first picture here, we can see that the angle A plus the angle B, when added together, do create a straight line, which means the size of angle A plus the size of angle B equals 180 degrees. Note that 2 angles which add up to 180 degrees are called supplementary angles. So it doesn't matter how many angles are there, they can add up to 180 degrees if they create a straight line. Notice now the use of these 2 straight lines, either side of the angle. So these imply the size. So it's the size of angle A plus the size of angle B equals 180 degrees. We see this in other places. So just remember that no matter what we're talking about, the size. Another important property of angles which we use to help us to find the size of missing angles is angles which are vertically opposite are equal in measure. Now it's important to note that this occurs when we have 2 or more straight lines. Often we think we may have 2 straight lines, but we actually have a full rotation broken up into different size angles. Here we have 2 straight lines which intersect, so effectively like an X, and here we know that two opposite angles are equal. So they've given us a little proof here. They say, well, A and C is a straight line, so they're 180, and B and C are a straight line, so they're also 180. So when we add all that together, we can basically say, well, if B and C are 180 and A and C are 180, by that logic, A and B must be equal. We could use a similar logic to prove that C and D are equal. So this is a nice, quick little piece to know as we're working through questions. We'll be able to say, oh, I know these two angles are the same because they are vertically opposite. So now let's talk about parallel lines that are cut by a transversal. So parallel lines are lines that will never meet. They are given to us in a diagram with little arrows to indicate that they are parallel. You can never assume two lines are parallel. So you're either going to be told in a question they are parallel, or you're going to be given arrows to show that they're parallel. So a transversal is a line which cuts across two or more parallel lines. In this first picture, we're talking about line L. So the technical term for line L there is a transversal. So what we get when we have two or more parallel lines and a transversal is we get two very specific types of angles. We get what's called alternate angles, named because they are, well, when you look at them location-wise, they appear on alternate sides of the transversal. So you can see that they're both between the parallel lines, but they're on opposite sides or alternate sides of the transversal. One thing you can look for alternate is the letter Z. So you can see our Z here. When you can see that letter Z, that means alternate angles. Alternate angles are equal in size. Other alternate angles in that particular picture will be this one, and you might say, well, that's not a Z. Well, it is a backwards stretched Z. Okay, so there's my two angles here. So corresponding angles then, they're given here, and you'll notice in this case we have five parallel lines, all indicated with their little arrows, and we have one single transversal, our line L here, and corresponding angles appear on the same side of the transversal and in corresponding sides of the parallel line. So here, our corresponding angles are all above the transversal but to the left of parallel lines. So the letter which we tend to look for here is the letter F. Now it'll be on its side, it could be backwards, but there's our little F here. Or there's another F here. So we have our F. So they are corresponding angles, and these corresponding angles are equal. So the last piece, which is a useful one to have, but sometimes students forget about this, and that's absolutely fine, but it will make your questions a little bit quicker. And they are that between two parallel lines, when we have a transversal like this, the two interior angles will add to 180 degrees. So you can work that out by using the logic of alternate angles. So if I was to use alternate angles, I'd say that this angle is equal to this angle, which is true, and because this one equals this one, I can say that, well, this angle here plus this angle here must add to 180, therefore this angle here plus this one must also add to 180. Similarly, you could use corresponding angles to talk about this. So this angle here is the same as this angle here. So by the same logic, we can work this angle plus this angle here must add to 180, therefore this angle plus this angle must add to 180. So there is ways to work around it, but like I said, it's a nice little trick to have up your sleeve to make the questions go a little bit quicker. So here's a nice little visual for you to see angles that relate to each other when we're talking about parallel lines and a transversal. There's even more here than we would have talked about it. They talk about an alternate exterior, which are the ones in orange. So they are an alternate angles, but they're outside of that transverse, or they're outside of the parallel lines as opposed to inside the parallel lines. The green ones here, same side interior, equal 180, so they're not equal, they both add to 180. And same side exterior add to 180. They have that nicely labelled transversal, so this might be too much for you, that's absolutely fine, but it can be useful just to visually see how things relate. So now let's look at an example which uses this. Just to note here, we have three a little bit funny looking letters, but what we have here are three Greek letters. They are alpha, which kind of looks like an A, beta, which kind of looks like a B, and gamma, which some people say kind of looks like a Y. So there are three letters that we're looking for. The fact that they're using Greek letters instead of just normal letters, that's absolutely fine. It doesn't impact on our question in any way. Do you note that we have three parallel lines here and they're not equally spaced? So we have two angles given to us in this picture and we need to figure out the other ones. So we're going to go for some basics first. Well, this angle here is opposite this angle here, which means that that angle here is 40. Okay, so be careful when you're using vertically opposite if there's more than two lines, so you don't get confused as to what is equal to what. Okay, so I'm going to then talk about alternate angles. So let's see this Z here. Okay, so my Z here means, well, actually, this is also 40 degrees. I can now work out my beta because beta plus 40 degrees is actually going to add to 180. So I know beta is actually 140 degrees. And I take a look at my picture and I say, does that make sense? And what I mean by that is, like, is beta an angle which is obtuse? And it is. So it's important to really keep on track of that, because if I got a number less than 90, I'd know something has gone wrong. So yeah, beta is definitely over 90 degrees, and that's the angle that I got, 140. So now, going back to what I know, I'm going to use alternate again. And I'm going to write in, well, actually, this angle here is alternate to beta, which means that's 140 degrees. So that means for me that gamma plus beta, or gamma plus 140 degrees, is equal to 180, leaving me with a gamma which is 40 degrees. And again, I'm looking at my picture, I'm saying, does that make sense? And I'm saying, yeah, it does, because that is definitely an acute angle. So the only one I haven't worked out so far is my alpha. So let's go back to that. So I'm going to change colours again. So I'm going to work with 115 because I haven't done anything with that yet. And I'm going to use the fact that I actually have an F. Now, my F is upside down, yes, but it is still an F, which means I have a corresponding angle here. So that's 115 degrees. So I have now got a triangle which is alpha plus 115 plus 40, and I know that that should add up to 180. So I know the angles I already have is 155 equals 180. So alpha is equal to 180 minus my 155. So alpha is equal to 25 degrees. Now, that is just one method to do that. That is not the only way you have to do that. There are many, many different ways you can work it out. You're going to be basing it off the same principles that we've worked through there, and you're going to get similar angles as we did there. You might get ones, you might get this one here, that's absolutely fine. You might get this one here and say, well, that's 40 degrees as well. So there's lots of ways that you can work. So this one here, 65 degrees. So if you want to work through it a different way, that's absolutely fine, but your answers should be the same. So now let's take a look at another example. If L1 is parallel to L2, so this little symbol here means parallel. So it just saves them giving us the arrows on the picture. Find the size of the angles alpha, beta and gamma in the following diagram. Now notice that the alpha appears twice, and what that means is they're both the same size. We then have our beta here, and we have our gamma up here. So because we know that they're parallel, we can go in straight away with a little bit of work with our alternate angles. So let's talk about our Z here. So because of the way this works, this angle here is the same as this angle here. So that's 73 degrees. Be careful here because there are a few transversals happening. It is easy for us to kind of get a little bit lost with it. So now I'm going to work with another Z. So from here I've actually discovered that alpha equals gamma. Okay, so whatever I get for either of them, I'll have the other straight off. So here we are with some lines in here already. We have 73 degrees, we have our 60 degrees, and we can actually fill in our third angle here because we know that when we add all them together, they should add up to 180. So when we do that, we figure out that this in here is 47 degrees. Now that might be useful for us in a minute, so we'll just leave that in there. The next thing I'm going to do is I'm going to try and look and see, well, where do I have some information? So we have a good few triangles going on here. So let's look at this particular triangle here. So in this triangle here, I know one of the angles and I don't know the other two, but I know that they're both equal. Remember we said alpha was actually equal to gamma. So I know if I add 60 plus 73 degrees, which gives us 133 degrees, and I take that from 180, which gives me 47 degrees, I now know that alpha plus gamma equals 47 degrees. But I also know that they're the same. So alpha is equal to gamma, and they're both equal to 47 divided by 2. So that gives us 23.5 degrees. Now, don't panic because you see a 0.5 degrees. That is absolutely fine. Change my pen color. It's absolutely fine. There's no problem with that at all. We don't see it much anymore, but this is an older question. So now that I know what alpha is, I can come along and look at this triangle here. And for this triangle here, we can say that alpha, which is 23.5, plus beta plus 73 should again equal to 180 degrees. And working through that, we get beta equals 83.5 degrees. So we use a lot of our properties of angles here. We looked a little bit about triangles, and we'll see that in a lot more detail in the next video. So now let's take another quick example here. We're only going to look at part A. We do this example again as we work through the triangles video. So they tell us to find the value of x. So notice here I have two parallel lines. Therefore, I actually know that this is 70 degrees here because it is corresponding, and this is 3x because that is also corresponding. So I'm able to use the properties of triangles, which is that all angles in a triangle add up to 180 degrees. I know that 2x plus 3x plus 70 equals 180 degrees. And it doesn't actually matter which triangle I'm looking at. That will be true for this little triangle here, or it would also be true if I took the bigger triangle. We'll look at that in a lot more detail as we work through the triangles in the next video. So we have 110 degrees here. So x 22 degrees.